Good afternoon. My name is John Archer. I'm a research scientist working here at EPA's Durham, North Carolina Research Facility, otherwise known as Research Triangle Park, North Carolina. I have a degree in environmental science and engineering, and I'm one of approximately 30 researchers working in EPA's research side with the Homeland Security Research Program. Today I want to tell you a little bit about what we do in the Homeland Security Research Program, as well as I'm going to show you around a couple of our specialized laboratories. The Homeland Security Research Program was established shortly after September 11th, 2001, otherwise known as 9/11, when we had the terrorist attacks on New York City, and then after that some envelopes with white powder were sent to certain locations that contained spores of Bacillus anthracis, which is the agent that causes anthrax. And so EPA, being the lead federal agency for drinking water and protecting wastewater systems, cleaning the environment after contamination events, the Homeland Security Research Program was formed. Welcome, here we are at our fluid modeling facility here in Durham, North Carolina. Behind me, you see a rainfall simulator. The rainfall simulator is one of our tools that we use for our Homeland Security research to be able to study fate and transport of spores that we mentioned earlier, and how they actually wash off surfaces if they're deposited in a wide area event outside. This rainfall simulator is obviously huge, as you can see, hopefully, how tall it is. It's about 27 feet tall. We can simulate rain events less than 1 inch per hour, all the way up to 4 inches per hour. So we can simulate both subtle rain events as well as simulating an intense rain event, which would be about 4 inches per hour. The important part of this is that we can do rain simulation and simulate wash off from surfaces indoors. We don't have to wait on an event to happen outdoors. And so we simulate that by using what we call coupons. You can see an example of a concrete coupon here. We can simulate asphalt, concrete, or other outdoor surfaces. We would inoculate, deposit spores onto the surface, put it in the rainfall simulator, and then simulate a wash-off, what would actually occur outdoors. Something else that you'll see in here is called a dristometer. This is an instrument that actually measures the rainfall intensity. It actually measures the rainfall droplet size as well. So you can see that inside the rainfall simulator. Up top, you can't really see it, and I'm not going to put the camera inside, but about 27 feet up, we have a nozzle where we generate the rain droplets. When we're generating the rain droplets, we can actually measure here, so we generate a curve. And I think we're going to be able to turn on the rainfall simulator here in just a second so you can see an example of it. What we do is capture the rainfall velocity droplet size with the dristometer. Here is an example of the rainfall right now. So you can see it generates a nice mist. It's actually sweeping out just a little bit. We have to make sure it stays dry. We can also change the size of that, change the intensity to, again, simulate different rain events. Hello again, everybody. Welcome back. Here we are in one of our other Homeland Security research laboratories. This large laboratory is called our aerosol test facility. And behind me, you see our large aerosol wind tunnel. When I say aerosol, I mean essentially a solid or a liquid particle that's suspended in air. So it could be things like fumes, dust, mist. It could be the COVID, SARS-CoV-2 virus particles in air, but anything that's in air that's suspended. And so what you see behind me is our large aerosol wind tunnel. This system was constructed years ago and intended to really test materials and test aerosol transport and aerosol sampling devices for some of EPA's national ambient air quality standards, primarily for what you've probably heard of, PM 2.5, particulate matter 2.5 microns. The interesting thing about this wind tunnel is it's one of the largest wind tunnels in the world. And it's also a recirculated wind tunnel. You can't see it. Right now you're looking at one side of it, but if we get a shot later on, you can see that it's basically a large rectangle. so it recirculates the air. So we can basically move air in this tunnel. We can generate particles of different sizes, and it could be an aerosol, it could be a bioaerosol, it could be a spore, anything like that. It could be a chemical particle as well. And what we can do is control the conditions inside the wind tunnel. So we use temperature and humidity control, and we can simulate certain conditions, control those conditions. We can introduce aerosols into the tunnel. And in a couple of our test sections here, this is what we call the human exposure test section. Very large, it's about 4 meters by 4 meters. And what we can do in here is use mannequins to simulate humans that would be exposed to a contaminant, and look at their potential exposure under different conditions to different aerosols.
Hello, and welcome to the US EPA's Research Triangle Park, North Carolina campus in Durham, North Carolina. My name is Matthew Pate. I am a mechanical engineer in our facilities operations branch. I also serve as our campus energy and water conservation manager, and I'd like to show you a few elements of our campus around here today. We share a 550-acre, mostly forested campus with the National Institute of Environmental Health Sciences and our utility plant, which you can't see right now through the forest, but it is hosted by the National Institutes of Health. They serve us an underground chilled water and high temperature hot water utility loop, as well as a pass-through for electricity into our campuses. We're currently standing atop our main entrance plaza for our main administration building and one of our large laboratory buildings. There are actually some classrooms below us. We host a lot of visitors every year, approximately 20,000 visitors for educational events, conferences, expos, and at any given time we usually have about 1,200 federal employees working here and about 1,000 contractors at any time. So I'd like to take a moment to take you around to a few of the different locations here as a sustainability and building infrastructure effort. During 2014, President Obama issued a presidential memorandum directing all federal agencies to outfit their work sites with pollinator habitats to the maximum extent possible. And this is our first installation on this campus since that issuance of that presidential memorandum. This is our National Computer Center, the front entrance of it. This used to actually be a spoil pile post-construction of the campus, so it sat idle for about 15 years. So this year, and last year and then this year, we've spent a lot of effort cleaning it up, and we intend for this to move forward as a chemical-free pollinator meadow. We're in late October and I still see numerous butterflies interacting with the plants around here. We're mowing a couple of cross pathways, and hopefully in the future maybe a couple of small native trees and benches for people to come out here and eat and relax in the lunch amongst the pollinators. Welcome to my favorite solar array on our campus. This is a thin film amorphous silicone photovoltaic solar array. These are flat, they adhere directly to the roof surface. They're literally glued on, each of these strips. Each of these strips is 50 watts. And all of the electrical wiring for this array is contained within these shrouds. And then they're connected to the side at the end, and then they're sent in the building for inversion to AC so that they're usable inside the building. The total size of this solar array is 55 kilowatts. I typically refer to this as enough to power 8 to 10 energy efficient American homes. And it was installed approximately 8 years ago, and it's still performing pretty well at approximately the 95% of its original capacity. We do see degradation over time. The sun degrades all materials, and however, during the first 10 to 15 years of a solar panel's life, we see very minimal degradation. And we've actually seen this one perform pretty well.